I know. So today we are starting to talk about function operations. Well, what in the heck is a function operation and why do I care? Well, we're going to read through problem number 1 and you'll see why you care. So let's say you are buying an item that's $100. You have 2 coupons you'd like to use. One is for $10 off your purchase and the other is for 10% off your purchase. The store will allow you to use both. You of course want the best deal, so you realize you can figure it out with function operations.
Function operation.
Well, see, funny enough though, whoever programs the cash register had to program in function operations. Because well, let me ask you, is it even gonna matter? Does it matter in what order you use these 2 coupons? So first of all, do you all understand the scenario? You're buying something that's $100. You have 2 coupons, 10% off, $10 off. They're gonna say, yeah, go ahead, use both. Does it matter which one I apply first?
Yes. Yes.
Not in this case.
Yeah, it does. Yeah, it does.
Well, let's find out.
10% of 90 is less than 10%.
Well, let's look at part A. If you use the $10 coupon first, then 10% off the remaining balance, how much would your item cost you? So if you use $100, $10 off first, and then 10% off, what would your final cost be? Well, $10 off gets us down to 90, right? And then you guys know the shortcut to do 10% off, right? Please tell me you do. Well, you can. Say it's a weird number. Say it's like 13% off. You know the, oh man, so much. Well, no, there's just so much I can teach you. Instead of saying I'm saving 10%, can't you think of it as though I'm paying 90%? So instead of finding 10% and then subtracting it from the total, I can do, instead of doing those 2 steps, I can just do 1 step. I can just figure out what 90% is. Isn't that the same thing? If you're saving 10%, aren't you paying 90%? Exactly. If something's 30% off, it's the same thing as if I'm paying 70%. So instead of doing 2 steps, if I just think in my head, oh, okay, I'm just paying 90% instead of saving 10. I don't have to figure out how much I'm saving. I just figure out how much I'm paying. So I take $90 and I find 90% of it. So this thing should cost me $81 at the end of the day. So part B asks us, do you think it would be the same final price if we did it the other way? 10% off first and then $10. So you have to answer that for yourself. Do you think it's the same amount or no? And then C, I want you to actually do it. So what if we did 10% off first or paid 90% of the total cost and then took off the $10? What's my final cost in scenario C? 80. There is a difference, right? Because if I do 10% off of 100, I'm down to 90. Right, but you think that this is irrelevant, but these are, oh, maybe. But also, this is just one scenario. They could have been totally, it could matter a lot. It could be, maybe you have a 30% off coupon and only $10. It makes a difference. Here's the other thing. When you say things like, oh, it's only $1, it's only $1, it's only $5, it's only $20, it does. And here's what I want you to imagine. In your lifetime, you're only going to earn so much money, right? Visualize all the money you're going to earn in your whole entire lifetime as like this big pile of gold, right? Every time you say, oh, it's just $1, it's just $1, it's just $1, your pile of gold just is dwindling, dwindling, dwindling.
Right,
You
can't take the gold with you when you're dead.
You're right. But I would rather have a big pile of gold to spend on what I want to spend on. Not just like, oh, whatever. Why should I pay Stop and Shop an extra $5? Why should they get it? Why shouldn't I spend that on my vacation?
May I use the bathroom with my extra $5?
I guess. That's the whole thing. Like, it makes no sense to just be like, you have to care. Okay, I get not caring about a nickel, fine. But, well, you say $1 now, but they add up. I'm telling you. $1, you see $1 on the sidewalk. Find me someone that's not going to bend down and pick up $1. You're going to pick up $1.
No, I was gonna say, my stepmom's daughter found $200 on the ground.
You see, I can't think of one person that I know of that wouldn't bend over to pick up $1. Maybe you don't bend up to pick up a dime. I do, but some people may not. But $1, you're gonna pick it up. Of course you are. Who wouldn't? You're crazy. Of course you're gonna pick up $1. What you do with that $1, that's up to you. Any Hoosers. So, back to function operation. Sometimes it does matter. Now, let me ask you this question. What if I had 2 coupons that were like $5 off my total purchase and $10 off my total purchase? Would that matter what order I use them in? No, that one doesn't matter because it's just $15 total off my purchase. What if they were both percent offs? What if I had like a 10% off and a 20% off? Does it matter what order I put in? Well, it doesn't matter. Think about it. The answer's no. Doesn't matter. Why? Why does it matter if it's a percent and $1 off, and it doesn't matter if it's 2% off?
No matter what way you do it. Like, if you add the percents together.
Kind of. It's basically because when you do a percentage off, it's really a multiplication problem. And it doesn't matter in what order I multiply. Same thing if it's $2 off. It doesn't matter in what order I subtract two things, as long as I subtract them both. But when you're mixing subtraction with multiplication, that matters, right? Because it matters in what order I subtract or add and multiply, right? Because if I did 2% offs, I think that's the next thing that I talk about. Okay, let's talk about it now. See, I know myself too well. I wrote this paper years ago and I forgot. See? I put it here. I know myself. All right, so scenario 2. Take the same scenario. You have 2 coupons. Now you have 40% off and 20% off. Doesn't this mean I get 60% off? If I have 2 coupons, one's 20%, one's 40%. Doesn't that mean I get 60% off? Right?
Yeah.
No!
You're being weird today. I don't understand.
It literally says it.
If I have 2 coupons, right, and one's for 20% off and one's for 40% off, do I get 60% off my purchase?
You can stack coupons.
Yeah, well, it depends on the store and their specifications. But assuming I'm at a store that will let me use 2% off coupons, is a 20% off and a 40% off together a 60% off?
No, you choose one first and then you do the other off the other.
Does it matter, the order? No, I just explained that. I don't know if you were listening. Or were you not here? Oh. See what you miss?
He wasn't supposed to run.
When it's 2% offs, it doesn't matter because they're both multiplication and it doesn't matter which way you multiply. It matters when you're mixing multiplication with addition or subtraction. So I'm still waiting for a good answer to my question. If I have 20% off and 40% off, is it 60% off?
No, it says wrong.
Oh, that's right. It's incorrect. Right? Because think about it. If you had 2 50% off coupons, does that mean everything's free?
Should be.
Well, take 50% of an item and then take another 50%. Is it 0?
75% off.
Right. It's right. So, let's try this one. If I took 40% off first, $100, I'm paying $60, right? 40% off 100 is $60. Now I would take 20% off 60, which is the same thing as paying 80%. So I just do 60 times 0.8. I'm on this one right here. I did 40% off $100. Got me down to 60. It's a new scenario. And now I'm going to take 20% off 60, and my final cost is 48. Right. Now I'm going to switch it. Assume I had taken 20% off first. That would get me down to $80.
Oh,
And now I'm going to take 40% off of $80. So that'd be 80 times 0.6. And I still get to $48. Sorry.
I'm so lost.
That's all right.
All I did was, in this one, I took off 40% first, then 20%.
Where'd the 80 come from?
Because now I switched it. I did my $100 item 20% off. And then, so that's 20% off. And then I took the 40% off. So when it's just percentages, you can see it does not matter. Order does not matter because it's multiplication. So in part E, I'm asking you, what is the total percent that I saved? Because it's not 60. Yeah.
48%?
Oh, you're close.
You said 49.
What did I save? I paid 48%.
Oh.
So I saved,
You saved 52.
yes, 52%. Now, that was easy. That's easy to figure out because my original item was $100. So if it was something weird, how could I figure it out? Well,
Give up.
Stupid thing where it's like 15% of this equals.
you can. So the first one I did 40% off of 100. So that's like paying 60% of 100, right?
Yeah.
And then didn't I take that answer and multiply
Wait, I
it?
was playing taking 60% off, like taking 40%.
That's me paying 60%. 40% off is the same thing as paying 60%.
Oh, I thought you said 60% of 40%. I was just saying. I got confused.
I don't know. I might have misspoke. But what I meant to say was taking 40% off is the same thing as paying 60%. Then I'm going to take 20% off, which is the same thing as paying 80% of that answer. So I just take that answer and I multiply it by a 0.8. That's why, do you see how it's all multiplication? So it doesn't matter in what order I do any of this. So, sure, why not?
Wait, so is it 0.6 times 100 equals something and then times 28?
Well, this gets me the answer if I do all of my discounts. I take 60% of 100, and then I take that answer and I multiply it by 0.8. Does that make sense? So that gets me down to the $48. Are you with me or not so much? What's 0.6 times 0.8 is 0.48. So if I'm doing 0.48 times 100,
I'm just confused on how you wrote it. Because there's like a comma.
oh, that's a decimal.
Oh.
Sorry. And that's a multiplication dot. Anyway, the whole point of this was to show you that function operation does actually matter in real life. So what happens when you actually go to a store that actually lets you use 2 coupons? Guess what? Their register usually will just put it, it doesn't matter what order you give that to the cashier, it's going to adjust it to make it out in their benefit.
And so when you have a percent and like dollars off, use the percent first, right?
Because you're taking the percent of the larger number. So yes, if you ever have the option, percent first and then dollars off. CVS is one of the places that will let you stack coupons like this.
And my grandma does them all the time.
You see?
She's like in there emptying her whole like purse.
The receipts are like 10 miles an hour.
They are. They're great. All right. Any Hoosers. So, am I going to make you do all these kinds of word problems like this? No, it's fine. So here's function operation when you're just doing the math, okay? So first of all, we have to remind ourselves about function notation. So if you look at number 2, remember f of x and g of x? F is just the name of the function. So whatever this letter is here, I'm just naming it. So I just know which one I'm talking about. Am I talking about f or am I talking about g? That's all. So the first thing, this is just the name of the function. This is just the variable that I'm using. Sometimes I replace,
Times the x.
It's not times. Function notation, the way you read this out loud is f of x.
Oh,
Yeah. So function notation, that does not mean f times x. This is the variable that you're using, and sometimes we replace that variable with a number, right? So if I want to find f of 5, I plug in 5 for x and see what I get out. So what would f of 5 be? Just out of curiosity.
for like, oh,
For this one, for number 2, what would f of 5 be?
23.
23, because I just take a 5 and I plug it in, I get out 20 plus 3 is 23. You don't do anything on the left-hand side. What would g of 2 be? 2, because I plug in a 2 for x squared minus x. Now, what is this? Find f plus g of x.
Squared plus 3x plus 3.
Yes, you're literally just adding the two functions together. That's it. So I'm just combining like terms. So I get x squared, 4x, and a negative x is just a positive 3x, and then a plus 3. That's it. Well, that wasn't so bad. If I wanted to do number 3, I just want to divide these two. So I literally just write x plus 3 divided by 2x plus 2.
You don't have to do it.
Nope. That's it. Try 5. 5, you have to be careful. Yep. Sure. Go ahead.
It would be x squared minus 2x plus 8.
Perfect. Does everybody know where that came from? Sorry. You have to take the g function, which is x squared plus 3, and I have to subtract all of the h function. So it's minus all of this, so it's 2x. So you really need to distribute that negative. That's how I get x squared plus 3 minus 2x plus 5. And then when I combine like terms, I get my answer. What does 6 tell you to do?
Multiply.
You gotta multiply. So since these are both binomials, what are you gonna do? FOIL! Everybody try 6 real quick. Did you get what I got? All right, pretty good. Let's rewind up to 4, because that one looks different than these other ones. What does that mean?
Multiply g by 2. Negative 2.
Yeah. And then I just, whatever that answer is, I would subtract h of x from it. So that's all this means. Take g and multiply by negative 2, so that'll be a negative 4x minus 8. And then I have to subtract all of h from it. So that'll now be a plus 2x plus 1. So my final answer is just that. Oops. Everybody okay so far? Yeah? All right. So, let's see. Okay. Let's jump to one like number 16. No, not 16 yet. Sorry. Let's do 17. What's that? What does that tell me to do? Yes! So, since I have a number now inside the parentheses, that's function notation for go to that function and replace x with a 6. And just tell me what comes out. So then I'll take that answer and I'll subtract whatever I get from h of 6. So g of 6 is just what? Isn't that 8? So I'll do 8 minus, what's h of 6? 24. So my answer would just be 8 minus 24, or negative 16. Do you see that? So if there is whatever is inside those parentheses is what you replace the variable with. It could be another variable, right? It could. Whatever is in there, you're just going to take it and dump it into the function. So when I look at 18, for example, there's a negative 3t in there. So what am I going to do? I'm going to add h and g together. And then, wherever I see an x, I'm going to replace it with a negative 3t.
That's so stupid.
Sorry.
You're just like adding new variables.
So, let's add the two together. I'd get x squared minus 3x minus 4. But now, I need to plug in negative 3t everywhere I see an x. So, I'll really have negative 3t squared minus 3. What was that?
Isn't that just 9t?
Yep. And now this you're going to have to simplify. So I get the 9t squared plus 9t minus 4. But there's my final answer there. Okay, Miss Sabia, this seems all right. But what in the world is number 8? What is that even talking about?
Oh.
I don't know what to do with that. What is that? Don't worry, I'll tell you. Or do you know?
Isn't this fun?
No. So I'm glad that you said that. There's a big difference between how 6 is written. See how it's h of x times g of x? The way that 8 is written, basically what this means is take the h function and put it into the g function. This, believe it or not, is what you were doing when you were taking 10% off and $10 off. You were doing what's called function compositions.
So h goes inside of g.
Right, whatever is inside the parentheses goes into the other one. So watch how this is going to work. I'm going to take all of h, which is 2x plus 2, and I'm going to put it in the g function in place of its variable. So instead of writing x squared minus 3, I write all of this squared minus 3. That's how I do it. So 2x plus 2 squared minus 3. You do need to do that out. It's usually just the division ones we kind of leave alone. So I have to FOIL that through, so that'd be a 4x squared plus 8x plus 4 minus 3. So I really get, as my final answer, 4x squared plus 8x plus 1. Let's zoom down to 14 real quick.
Wait, what did
What? I'm sorry.
wait, what's the final answer?
Right here.
I can't see
Oh,
that.
sorry.
Oh.
So jump to 14. This one now is function composition with a number. So what does this mean to do?
Oh,
You-
7 for x and then f.
In the f function.
Yeah, that's what I got. And then f into g.
Right. So you always work from the inside out. So I'm going to take 7 and I'm going to put it into the f function. I'm going to get some answer. Once I get that answer, I'm going to put that answer into g. So that's how this works here. So let's put 7 into f. So f is this one. So I get 27. Right? Do you all agree? Now I'll take 27 and put it into g. So my final answer is
25.
Wanna be
25
tr-
minus 1 is 27.
and then take that and put it into this.
27 minus 25.
24. Now, one last thing that's super confusing, and I don't know why this is the way it is, but it is. There's another type of notation to write the same thing. And it's not on this sheet, but I need you to see it, because what if it's on the MCAS or probably not, but you never know. Or SATs, who knows. Another way to write this whole thing is to write with an open circle. G, open circle, F, and then put the 7 like that. Or, I'm sorry, like that.
We did this at the very beginning of the year.
Oh, did we? Oh, good. That's another way to write just like that, totally equivalent. It's this little open circle. If it's a closed dot, like if you,
Kind of just saying like G as F.
yes. If you look at 22, 22 is that's a closed dot. So you're literally multiplying those two. It's super confusing because a closed dot is multiplying and an open dot is totally different. So if you see a little open dot, that means the same thing. Take 7, put it into the F, and then put the F in the G. Okay. So